hydronium ion concentration, hydroxide ion concentration, the pH, and then is it acidic, basic, or neutral? So some of this we did last time, but some of it we didn't. So let's look, for instance, at this fourth. We're going to skip around a little bit here, but let's look at this one right here. How do you figure out the pH if that is the hydronium concentration?
This is formula like minus log.
Right.
Yeah.
Yeah.
1 per 10 minus 10.
Yeah. So you take the negative log of that. And what is the negative log of that? You shouldn't necessarily need a calculator for this one because it's an easy one.
This will be
12.
Right. It'll be 12. Yeah, because that's the exponent. So we can say that the pH of the solution would be 12. And is that acidic, basic, or neutral? Let's go check out the scale.
It's going to be basic.
Yeah, so here's our pH scale. Right, neutral is about 7, which means basic is above 7 and acidic is below. And really neutral is like between 6 and 8. But we've got basic, so that this is at 12, which is quite basic. So this is basic. Right. So then how do we fill in that last slot on that row? How do we find the hydroxide ion concentration?
This is like 1.0 multiplied by 10 minus 14, yeah?
Right.
And then we have to divide by H3O.
Right. So we had talked about last time that there is this pH and the pOH, and the sum of those two is 14. We can also do this with the concentrations. It just looks a little bit different, and it's multiplied instead of added. So we can say that the hydronium ion concentration multiplied by the hydroxide ion concentration is 1 times 10 to the minus 14. That's saying the same thing. It looks different, but it means the same thing. So then if the hydronium ion concentration is 1 times 10 to the minus 12, what's the hydroxide ion concentration?
It will be 12 minus 14.
Right, so what would that be then? Right, so the hydroxide ion is then 1 times 10 to the minus 2 molar, which means the pOH would be 2. Now, if the numbers aren't easy like that, like the previous one, which is 2 times 10 to the minus 5, that's when we probably want to use a calculator instead. I can show you how to do it without a calculator if you want, but if you have a calculator, you can use that.
Yeah. 0.5 by 10 minus 5.
Oh,
Right.
I have this. So if we write only 2 minus 2.
That's wrong, because that is the pOH. That is this, which is the negative log of that. If we want the concentration, which is this, the actual concentration, then it must be in this kind of a form, okay, because it's a small number, it's a smaller number. Now, you don't have to write it in scientific notation. That makes it easier for the pH, but we could say here 0.01. That's the same as 1 times 10 to the minus 2. Just in regular notation.
Because with this number, I I feel it's not done. Yeah. I see it like it's not done.
Okay.
We should have a smaller number.
Okay, so you can keep it like that if you like better. Yeah. All right, there's one more piece of this table that we haven't really talked about yet, and that's how to go backwards. So take a look at the second line. The second line here, we have a pH of 3 and no other information. We can probably figure out acidic, basic, or neutral pretty quickly here. So what do you think it is? acidic, right? 3 is on that low end of the scale, so that's going to be acidic. Right. Now, how do we figure out the hydroxide and hydronium concentrations if we just have the pH? How do we go backwards? What's the opposite of a log? Kind of. So remember that the pH is the negative log of the hydronium ion concentration. So if the pH is 3, how do we figure out this? How do we solve for the hydronium ion concentration?
Multiply by 10 minus 3.
Right. So that means that we put that 3 up on top of the 10 thing. So the hydronium ion concentration here then will be 1 times 10 to the minus 3 molar. You see how that works? We took that pH number and we just put it up here in the exponent. So then the hydroxide ion concentration will be that subtracted from 14. So 14 minus 3 is 11. So the hydroxide ion concentration would be 1 times 10 to the minus 11.
So did the subtraction work in each example?
Yes.
We have to minus.
It works in each example, but when the numbers get a little trickier, we need our calculator to help us with that sometimes.
Can you give us?
Yeah, so let's look at the last line, the very last line. The pH, instead of 3, it's 4.62. So is that acidic, basic, or neutral?
Acidic.
Yeah, that's acidic. Still acidic. We can answer that one.
We will have this chart for acidic and basic and this one.
No.
So we just know that the line.
Know that the middle is neutral, 6 to 8. Below 6 is acidic, and above 8 is basic.
So 6.5, it's neutral?
Yeah, I would call that neutral. And again, this is there's no absolute line. Sometimes it is a little different, but for us, we will say that. Yeah. Okay, so let's look at those concentrations. Now, we can use the same technique for a weird number like 4.62. We could say this one should be 1 times 10 to the minus 4.62. Okay, but that's not really proper scientific notation. We don't like to have that decimal in there. So we can use our calculator to help us get rid of it. I need a little more complicated calculator here, but I think I can do it. Here, okay. So I can say 10 to the minus 4.62. Oh, I have to do that like that. Yeah. So 10 raised to the power of minus 4.62. And the calculator tells me that is 2.4 times 10 to the minus 5. You see where I get that?
For me, it's different.
Even like that.
0.0002.
Yeah.
2.39.
Yeah, times 10 to the minus 5. And let me show you how that is what you got. So let's call that 2.4 times 10 to the minus 5 molar. So that's the same thing. Now, what that is also the same as is the non-scientific notation number. Remember that 10 to the minus 5 tells you 5 decimal places away in the number. So we can also write this as 0.00024, right? 1, Where's it? 1, 2, 3, 4, 5.
So they are same.
And that's okay. On an exam or whatever, you never have to use one thing or the other, scientific notation or decimal notation. You can use whatever you want. Those are just different ways of saying the same number. Now, to get the OH concentration, the hydroxide concentration, we would do the same thing, but again, with some trickier numbers. So we might subtract from 14, 4.62. So 14 minus 4.62 is what, 9.8, 9.38? Yeah, okay. So again, we have this kind of weird number here. So we should calculate that to get the correct number. So 10 exponent negative 9.38. So we've got 4.2 times 10 to the minus 10. And so that's a better way of saying that. 4.92, or 4.2, sorry. 9.2. Now I got problems here. Let me just try that again. 4.2 times 10 to the minus 10 molar.
How we can get it from that?
Let me see.
I also can do it.
I do my best.
So you got the 9.38?
Yeah.
All right, so then
Yes,
you're going to go. No, it's just like this. You're going to go 1, and this is times 10 to that. So 1 times 10 to the minus 9.3.
You got it.
Yeah.
Delete it.
I see, okay. Minus. Okay, it doesn't like that, that's fine. Do it another way. We can do it just with this part. So we can go 10 to the minus.
I have something like that.
Or, yeah, so that's okay, that's the same. If you want to put that in scientific notation, I think you would need a different calculator.
Yeah.
Do you try turning it on its side? Sometimes it gives you a different calculator.
Basic and
So you can count it yourself. Like, go back to that number. So then you can say, all right, 4 times 10 to the minus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
so 4
So you move that decimal place over. How many places you have to move it?
minus 8,
So from here we will start, say, the basic, like
Right.
two. But here we will say like.
Well, we would say this is neutral, kind of. This is all neutral.
Okay, until
8. So yeah, it's 7.5 or 8.
This is to be basic. But here's will be like until the middle. Or
Yeah, I would say something like that. Did you get it to work on your calculator? There's two ways to do it on this one. You go 10, and this is the power, and 10 to the minus 4.62. Okay, that's one way to do it. Or you can go 1e minus 4.62. Oops, I did it that button or something. Oh, because it doesn't like the decimal, so you can't do that.
Yeah.
So you gotta do this.
This.
Yeah. All right, so to practice that now, let's pull in one more chart from the book.
How about the first one?
Oh, did we skip one here?
Yeah.
Oh yeah, okay. So see if you can do the first one. And the third one, because we skipped that too. So you try to do the first and third ones to fill that in. Yeah. Okay.
I think the third one is hard, like because it's two. I don't know what I mean. Two. Yeah.
Okay. Let's take a look at that. So the third one, yeah, with that 2 there, that makes it more difficult to just look at it, right? So we really need to calculate that one on a calculator. So we would say, on this one, you have to put the number in first. So 2 oh, whoops, no, not like that, okay. This is not the best calculator for doing this. So 2 times 10 to the minus 5. And then we would take the log of that and make it negative. So we get 4.70.
Log to. What can I do? The log minus 5
Yeah,
log.
that's right. So then the number, the 2 times 10 to the minus. Because it's close, but
But they didn't do
but because of the 2, it should be 4.7. All right. So then to find the hydroxide ion concentration, we would do the same thing from 14 from here, or we can just do from here with dividing. So we can say 1 times 10 to the minus 14 divided by this. Depending on your calculator, it might be easier to do it one way or the other. On my calculator, that's going to be difficult. So I'm probably going to do 14 minus 4.7 to get 9.3, and then raise that to the 10th power. Whoops. Try that again. 9.3, negative 9.3, and raise it to the 10th power. And that'll give me 5.01 times 10 to the minus 10. That's not right. Everything's got to be between 10 to the minus 0 or 10 to the 0 and 10 to the minus 14. So this should be 5 times 10 to the minus 10. So how did you do it? Yeah, because this doesn't, it's not doing the order of operations properly because it's dividing by 2 and then multiplying by this. So you need to put parentheses. See that? So it puts them all together. So then this first one would be kind of completes that table. All right, let's take a look at, we'll come back and practice more of this. We'll have time today to do some practice problems for the rest of the chapter. But I want to look at a couple other aspects of acids and bases that we haven't gotten to yet. Just a couple little things. So first, we've got this issue of acid strength. This is a common area of confusion because when we talk about acid strength, we think about it in terms of our own experience with acids. So when we think of strong acid, we think of something that is dangerous, something that burns us, something that eats through the floor, or something, you know, like acid in the movies. But in chemistry, when we talk about strong and weak acids and bases, what we're really talking about is electrolytes. So when we say a strong acid, what we really mean by that word strong is that this acid is a strong electrolyte, which means that it breaks up into ions in solution. Remember we did the test with the light bulb and the HCl, I don't know, well, maybe you don't remember, but the HCl made the light bulb go on. So that was a strong electrolyte that could carry the current. The acetic acid did not, or just did a little dimly, because acetic acid is a weak electrolyte. So we say that we call HCl a strong acid and acetic acid a weak acid. But that doesn't mean that one is more dangerous than the other. They both burn you and have problems or whatever. Acetic acid in many ways is more dangerous than HCl, even though it's called a weak acid. So when we say strong acid or weak acid, we are talking about how this thing breaks up in solution. So HCl, when it reacts with H2O, we usually make these kind of double arrows talking about how acid-base reactions go back and forth. So the HCl goes in the acid and it breaks up into ions. The H goes with the water to make hydronium, and the leftover chloride is chloride ion. Now in this particular situation, rather than making an even double arrow like this, what's more correct for this particular example is to say mostly this reaction goes forward and maybe only a tiny bit goes backwards, but almost insignificant. We can really just say this reaction goes forward. That is, all the HCl in solution is going to break up and form ions. That's what we mean when we say strong acid. A weak acid an example, like I said, is acetic acid, which is, this is the formula of it. We can draw the same equation. Makes hydronium again, and then this is the leftover ion. Oops, not that. That's called acetic acid. And this time when we think about how those arrows work, this reaction is going to go more to the left than to the right. So acetic acid in water only forms a little bit of ions. You won't. So not necessarily. I'm going to give you a hint as to how you will figure that out in a minute. But that's a tough question. Yeah. But mostly the thing that I want to emphasize here is that strong and weak is talking about the chemical behavior of breaking up into ions in solution. It's not talking about how much it burns. That's called corrosive. It's not talking about how reactive it is, chemical reactions. Good example is HF, hydrofluoric acid. That is technically a weak acid. It does not break apart in solution very much. But it's one of the most dangerous acids that we use regularly. It can eat through glass, so you can't keep it in glass containers because it just dissolves the glass. It eats through rocks. That's kind of the cartoon acid that if you spill it, it will eat through the floor and then go to the next floor and the next floor. You know, it's not good stuff. It's also really poisonous. It kills people. It can dissolve a body more or less. So that's bad stuff, but it's a weak acid because of how it behaves in solution. It's not a strong acid. So that's this part. Now, to your point, how do you determine if an acid is strong or not? There's really one hint, and we can check on Blackboard. I don't think you have to know these, but we'll check to make sure. There are only really 6 common strong acids. And these are acids that break up completely into ions in solution. You have hydrochloric acid, hydrobromic acid, and we'll talk about naming acids next. Hydroiodic acid, and then there is nitric acid, sulfuric acid, and perchloric acid. So there are only 6 acids that are considered strong and that they dissociate completely in solution. They break up in solution. Anything that's not on that list is a weak acid.
So if we see like this stuff in the any way, like on right or left, so we will plug that.
The arrow, yes.
The lines.
Right. That this is a strong acid and it will make ions completely. But before I forget, let's check Blackboard because you might not have to know all of those. This is always a good thing to check when you're studying. If you go into the acids and bases section, okay, so it just says, state the difference between a strong and weak acid, and strong and weak base, and given 3 examples of strong acids and 2 examples of strong bases. So you don't need the whole list, just those 3. I'll circle those on here. So you need to know this one, this one.
So the lines will be drawn for them or up, like
Yes, to the right,
the first example.
fully, the first example, right, yeah. Okay, base strength kind of goes the same way, but bases are usually salts, like sodium hydroxide, calcium hydroxide. So any salt, any hydroxide that breaks up in solution that is soluble is called a strong base. All right, so the next part here, we're going to look at how we name acids. There are 2 categories of acids that we're going, 2 categories of names. So I'll draw them side by side. First is what we call binary acids. And these all have the form HX, where there is a hydrogen and then some other atom, just 2 things. Now, generally the acids are named by based on their ions. So we look at what that X is, and then we make an acid out of it, and then we name the acid. So if we think about chloride, chloride has a -1 charge. So if we want to put some hydrogen with it, we would make HCl. And then we would call that hydrochloric acid. So chloride becomes hydrochloric acid.
It's strong.
And that's a strong acid, right? So if we had a bromide ion, the acid that makes would be HBr. And what do you think the name would be?
Hydrochloric.
Yeah.
So this is like strong acids here.
Yeah.
So each strong acid have IC in the end of the name here.
Right. All the acids that we're going to look at have this IC at the end.
But if we switch,
Yeah.
like from bromine to only bromine, so it will be weak. Or doesn't matter?
No, it's still a strong acid. Hydrobromic acid will always be strong acid. Okay. So you get the idea here. Fluoride becomes HF, which is, what's that called then? Hydrofluoric acid, yeah. These are not that difficult to name, but the tricky part is when they are in with everything else. So you just have some question that says, name this thing, and it says HF, and you think, oh, maybe I should call this hydrogen fluoride or something like this. But really, we need to recognize that if the hydrogen is there, we should name it like an acid. So it should be an acid. It should be hydrofluoric acid.
And when we do the bonus,
Hmm.
like before they ask us like write the equation. So if they write like a hydrochloride,
Mhm.
It will be HF.
Yeah.
We should know that.
Right.
And how much the charge this will be separate?
Well, it's always the same. Hydrogen is +1, is always +1 in these types of compounds. And the other ion is whatever the other ion is. So it's in this column, so it's -1. Yeah. Now, the other category of acids are named a little bit differently. We call these the oxo acids because they have oxygen in them. So the binary acid is just hydrogen and then one other thing. The oxo acid has oxygen also. And they come from the ions that have oxygen. So NO3 is, what's that ion? NO3 minus? Yep. Nitrate? Yep. So its ion would then be, or its acid would be HNO3. And with these kinds of acids, for whatever reason, we don't put the hydro first. So this becomes nitric acid. Nitric acid. What's this ion? Yeah. So then its acid, because it's -2, it needs 2 hydrogens. So it'll be H2SO4. And this one is called sulfuric acid. So it goes back to that sulfur name with the sulfuric acid.
All the time we will I see.
Yeah, right. This one, this ion, you don't know this ion, but this is called acetate. So then its acid is called acetic acid. I don't think you need to know that formula. Let's check Blackboard again when you're finished writing. Flip back and take a look at it. Yeah. So you need to know sulfuric acid, hydrochloric acid, and nitric acid. And then, yeah, just those 3.
Hydrochloric, sulfuric, and
So this one, hydrochloric, nitric, and sulfuric.
This charge is not. They will ask us to balance.
No. We're just talking about the
Yes.
names. Yeah. All right, so the last thing that we are going to look at in this chapter is something called a buffer. Buffers. Have you ever heard of this, buffers or buffering solutions?
this is like stabilization of pH.
Right, yeah, exactly. So buffers we'll say they're resistant to pH change. And we'll see this a little bit in the lab on Wednesday. let's say you have a beaker with some water in it. And you put in a few drops of HCl, a few drops of hydrochloric acid, concentrated. Concentrated means like saturated, the most you could put in there. Water by itself is what pH? Pure water?
Just 2 or 3 others.
7, right in the middle. So pure water has a pH of 7. If we put in a few drops of HCl, that makes a huge difference. Even just a couple drops are going to change that pH, drop it probably down to 1, or maybe 3 or something. But really, really drop it down. Just with a few drops of HCl. A buffer solution is a little different. It would be the same the other way, by the way, with base too. Now a buffer, you can control what pH it's at. Let's say we have one that is at pH 7. If we add a few drops of concentrated HCl to that pH 7 buffer, we're going to have pretty much the same pH. Yeah, maybe it increases a little tiny bit. Whoops, decrease a little tiny bit because it's acid. So maybe it just goes down a tiny bit, but it still pretty much stays the same. That's the advantage of a buffer. A buffer is a kind of solution where you can add more acid or add more base to a certain point, but the pH stays the same. And it works because of this going back and forth with acids and weak bases. Remember back up here when we talked about weak acids and bases? The weak acid here is mostly staying this, right? So if you put in some acid there, what happens is the acid's going to attach to one of these molecules and go back and form this, which doesn't affect the pH of the solution. So even when you add acid, you don't change the hydronium ion concentration. And if you don't change the hydronium ion concentration, you don't change the pH. So that's how buffers work. There's a little bit more information in the book. I don't think we need to go through all the details again, because all it really asks here for is the definition of the buffer. But just to kind of see a picture of it here. So that's kind of what we talked about, that if you have some water, you add a little bit of acid, the pH goes way down. A little bit of base, the pH goes way up. If you have a buffer, it only changes a tiny bit. And if you're interested in why that is, you can kind of look at this, how adding acid or base affects this, but doesn't actually affect the pH. If it's not interesting to you, you can skip it. That's fine. But what's important about buffers is in physiological situations, like in the blood. The blood has a very narrow pH range. Your blood has to stay in that range, or it causes big problems. And as you can see, that's a really narrow range. Just 1/10 of a pH scale number, pH value, whatever. So not a lot of room for error there. So that means your blood has to be highly buffering, because there are situations where your blood is going to experience some acids and bases. I mean, if you take a medication that gets in your blood, that's an acid. Stuff that you eat, whatever, if it gets into your blood, that could be change things from acid to base. Does anybody know, how does your blood regulate its pH? How does the blood control the pH? What kind of acid is in there that controls it?
I know we have some buffers inside the.
Yeah, so what creates the buffer? What?
The small part. I know it's another thing.
Okay.
So like or something like that, like some chemical is controlling.
Glucose.
Yeah.
That's blood sugar.
Not
that one? Okay. All right, I'll assume you know what it is, but we'll talk about it. It's actually carbon dioxide controls it from breathing. So what happens is carbon dioxide gas from breathing reacts with water, so it dissolves down in your lungs, in your blood. And when carbon dioxide dissolves in water, it forms carbonic acid. Carbonic acid is a weak acid. So in solution in the blood, the carbonic acid goes on to do one more reaction. Because it's an acid, it reacts with a little bit more water to make hydronium, which gives us acidity, and bicarbonate. Now this, because it's a weak acid, make sure I'm doing this right. Because it's a weak acid, we're going to actually have this going mostly this way. So we're only forming a little bit of hydronium and just enough to keep our body at that right pH. So if more acid comes in, then it can form more carbonic acid, which stays the pH, which keeps the pH constant. If basic stuff comes in our blood, then it can form more bicarbonate, which also stabilizes that pH. So having that buffering capacity gives our blood that stability. Now, what can happen when that goes wrong is that what often causes that to go wrong is having too much or too little CO2. So if you have too much CO2, that's going to create more carbonic acid, which makes your blood more acidic. And the name for that condition is acidosis. When you have too much CO2 and your blood is too acidic, we call that acidosis. And that can cause all kinds of problems because the various chemical reactions, the metabolism and things going on is very pH dependent. So if you get out of that range, it starts to mess with all those processes and cause those problems. The other extreme is if you have, give ourselves a little more room down here. If you have too little CO2, not enough CO2, your blood starts to get more basic. So the pH raises. And this is known as alkalosis. since your CO2 is controlled by your breathing, your CO2 level is often controlled by your breathing, a really common way to get into one of these conditions is by not breathing properly. So I think there's a problem in your book, and you can see here what happens when you have these different acidosis and alkalosis conditions. So it can be caused by breathing. It can also be caused by metabolism, like something's not working in your kidneys or whatever. But let me pull up this problem here so we can take a look at it. So this is a good. Interesting picture of that, but it says sometimes during stress or trauma, a person can start to hyperventilate. You know what that is? When you breathe too hard, like, and then you get all faint and you fall over and whatever. So if someone's doing that, they might say, hey, breathe in this paper bag like this, right, to stop that. So how does that happen? If you are hyperventilating, if you're going, what's happening to the blood pH and why?
Losing more.
Not oxygen. You're losing CO2. So that's, a lot of people think that it means you're not getting enough oxygen when you're doing that, but it's the opposite problem. You're not getting enough CO2. You're blowing it all away. And so how does that affect the blood pH?
It will be weak.
Yeah, so if CO2 is low, does the blood pH go up or down?
Down. The blood
The blood pH.
pH will be up.
Right. So if there's not enough CO2, that means you're not creating enough acid in the blood, so the blood is too basic. So then that means that the pH goes up. So when that's happening to somebody, you want them to stop expelling so much CO2, keep more CO2 in your body, and the bag helps you do that. So, and actually, I think it's been shown now that it's not that the bag, like, it's not because the bag is holding the CO2, it's mostly because you just need to calm down and focus on breathing, and that's what the bag does. But you get the idea that if you are not breathing properly, that can affect your blood pH.
And how about the concentration? Will be less or it doesn't matter?
The what?
The concentration.
The concentration in the blood?
Yeah.
Yeah, so the hydronium concentration in the blood will go down because it's not producing enough carbonic acid, not enough CO2 in the blood. Okay. All right, so that's pretty much the chapter. Let's take a look at some of these problems and practice doing some of this for a little bit before the quiz on Tuesday. Thank you. So one of the things I always like to ask are some of these issues of conjugate acids and bases. If you go on and take organic chemistry, that'll be a big issue as well. So can you look at these acid-base equations and talk and define the conjugate acid-base pairs? What do you think? Remember, acid and base has to do with what is it doing in the reaction. So if you got a problem like this, you should be able to label the acid and the base on each side. So remember the definitions. You need the definitions to be able to sort these properly. That the acid is losing hydrogen and the base is gaining hydrogen in the reaction.
An H will be
Is what? Which one's the acid? An A?
and O.
Yeah. Yeah, right.
And the basic H will be H2S.
Yeah.
So they usually want to see the plus and minus here.
Mm-hmm.
So it's a minus, it will be acid, the basic.
Usually, yeah. That's not always true. So you really have to look for where the hydrogen is going. So in this case, in this first reaction in A, you can see the hydrogen is jumping from here over to there. Because on the other side, hydrogen is missing from here, and there's now 2 there. So that tells us that this one is the acid, and this one is the base. The acid is losing the hydrogen, the base is gaining the hydrogen. On the other side, we need to start on the right and look going right to left. In this case, the hydrogen is on the sulfur and jumping over to the NO2, if we think about it starting on the right and going to the left.
So it's really the opposite thing.
Yeah, so we'll have now, this is the acid, and this is the base. Because the acid has to have hydrogen. The acid has to lose hydrogen. So now we can pair them up. And we can say, all right, which one is conjugates, acids, and bases? Well, the conjugates are mostly the same molecule, but only different by 1 hydrogen. So this and this are going to be conjugates. The conjugate acid, the conjugate base. And then this one and this one are conjugates, conjugate acid and conjugate base. They only differ by 1 hydrogen, by a hydrogen ion, H+.
Can you do that second one?
Yeah, so let's look at the second one then. We've got HCl and OH minus hydroxide. Again, we track where that hydrogen is going. So going right to left, where's the hydrogen going? Yeah, it's coming from here and it's going over to there. So that means this is the acid and that's the base, because the acid is losing the hydrogen and the base is taking the hydrogen. So we can also pair up these with their conjugates. When that hydroxide takes the hydrogen ion, it becomes H2O. So H2O is the conjugate acid. When the HCl loses its hydrogen, it becomes chloride, and that's the base. So in any acid-base reaction, each side will have an acid and a base. And the acid from one side is the conjugate of the acid from the other side, so they're together.
Can you spell active?
What?
The word. Yeah.
Conjugate?
Conjugate.
It's here, yeah.
So first we have to determine the first part of the reaction, and after that we can.
You can start on either side, whichever side is
Just figure out which
better.
one is, let's say, the taste.
Yeah. Mhm.
H2S would make your
Right. Whichever one is clearer to you. On the left side, for instance, on the second one, HCl, we know that molecule is hydrochloric acid. So we can be reasonably certain it's going to act as an acid. So that might be another way, another clue there. But looking for that hydrogen will always work. All right. So let's practice just drawing the conjugate acids and bases. There are these nice practice tables here. Let's see, where are they? Oh, I'm not in the right spot here. And there's some practices in the book too you can look at. We looked at some of these last time. Where are the conjugate acid base? Oh yeah, here. So let's see if we can complete this table. We did this last week. We did a little practice with this, where we see one as the acid, and then we can get rid of hydrogen and make the conjugate base, or we can start on the base and add hydrogen to get to the acid. And remember, we're dealing with hydrogen ions, H+. So we have to add or subtract the atom, but we also have to add or subtract the charge, the +1. So give that a try. See if you can fill those in.
Why do we have here H2PO4 and minus only one?
That's the formula of that ion.
But if you have two hydrogens,
Mhm.
so you have to have two PO4 or not?
No, that's right, because PO4 is a -3 ion. So if there's only two hydrogens, it will be -1 overall. Like -3 + 2. But anyway, that doesn't, for the problem, you just need to figure out what happens when you add another hydrogen here to get the acid. So do you, those? It's close. Think about your charges. All right, so filling these in then, the conjugate base of water, we remove a hydrogen, and since we're removing something that is +1, what's left over is minus. So this is going to be hydroxide, HO, or OH, same thing. But it needs to be -1 charge. Okay, going the other way, Cn- is called cyanide. We add the hydrogen to that, so it becomes HCN. And what about the charge?
Plus.
H1, yeah.
Yeah, it'll stay neutral now because it started in minus, so now it's neutral. All right, HNO2, that's called nitrous acid. Right, so we're going to take the H off, and that's going to make NO2 minus.
I thought about like a trust.
Yeah. And then the last one, H2PO4, dihydrogen phosphate, we've got, add one more hydrogen, we get H3, and then that one's going to be neutral, right? Because we add +1 to the -1 charge.
So for conjugate base, we don't need charges like 2, 3, or 1, only minus, yeah?
It could be whatever, it could be neutral, and the conjugate acid could be +1.
PO4 has a charge 3 minus, yeah? But for conjugate base, we have only 1 minus.
Yeah, because there are already 2 hydrogens there too. So it's not just PO4. But we could have also asked the same question. So we could have said, oh, I'm out of room here. Let's see. Let's continue our table with some other examples. What if I put conjugate base NH3 or acid HPO4 2 minus? Can you fill in those blanks?
NH3, it's base, yeah?
Yeah, so if NH3 is the base, what's the conjugate acid?
It will be NH4 plus.
Right. So it's not always neutral, but could be plus or even could be minus. And then in the last example, HPO4 2 minus, that's the acid, even though it's minus in this case. So what is the conjugate base?
-3.
Right. So it would just be PO4 without the H with -3.
So the rule for this, the conjugate will be all the time -1.
From the others, yeah. From the other one, yes.
And for the acids will be +1.
Right.
But if the number like it's never happened like a -2 or +2, like between.
Right, right. Always just one,
Yes.
because you only move one hydrogen between the two. Yeah. All right. So quiz on Tuesday, you can expect. Did I go too fast? Sorry. You didn't think we were done yet? We're almost done. You can expect this, making conjugate acids and bases, writing acid-base equations, calculating pH and hydronium ion concentration. That's it.
Can we do that calculator?
Yeah.
Thanks.
Let's try another calculation.
And when we write the chart, we will write it like that for acid and base, like that.
Right. All right, so let's take a look at this one. Solution X has a pH of 9. Solution Y has a pH of 7. Which solution is more acidic? Wait, one vote for it. Right.
And this is this.
So which one is more acidic?
It will be
I don't know. No.
Yeah.
9.
Right. Well,
9 no.
remember that it's true, 7 is neutral, but that can still be more acidic than something that is basic. So it's a scale. Any lower numbers are more acidic than higher numbers. So a pH of a solution with a pH of 12 is more acidic than a solution with pH of 14. But they are both called basic.
So the numbers would be more acidic.
Right. So Y is more acidic. What is the hydronium ion concentration in each? How do we find that from the pH?
This is like we have to divide 1 per 10, yeah, minus 14,
Mm-hmm.
and dividing by the 9 per.
Well, careful here. That we're jumping ahead, I think, to part C. So the hydronium ion concentration in each, X, the concentration in X will be 10 to the minus 9 molar, right? And the concentration in Y will be 10 to the minus 7 molar. So then the hydroxide ion concentration is when we subtract from 14. So the hydroxide ion concentration in X is 10 to the minus 5 molar, and the hydroxide concentration in Y is 10 to the minus 7 molar. No?
Like how you figure out, like first you write why you write X as a 9? Because the X has a pH,
Yes.
but the question asks about H3O.
Yes, that is the concentration of the hydronium ion. So it's what we were doing, the same thing as what we were doing here. Right? So this was the hydronium ion concentration. So if a pH is 8, the hydronium ion concentration is 1 times 10 to the minus 8 molar, or just 10 to the minus 8, because it's 1 times, it means the same thing. Then the OH, the hydroxide ion concentration, will have the rest of the other exponent subtract from 14. So that is another way of saying this same table, that other question. Yeah, so just make sure you're going through the homework in the chapter so you have practice with both of those things. And then you can see it.
And the zones will be the middle one, yeah, the chart. So
Right. Right. So 9 or 14 minus 9 is 5. So the hydroxide ion concentration is 10 to the minus 5.
that's the one.
So here, try it again. We are past time, by the way, but I don't think there's anyone else coming, so we can keep talking as long as you want. All right, so try it again. No, we're not doing the titrations. There's not a lot more practice of this, is there? Oh, here. All right, so we're going to calculate the hydronium and hydroxide ions for solution with the following pH values.
first one, we can use this the log.
Yeah, well, it's the opposite of the log one. So we use the log when we are given those concentrations and we want to find the pH. If we have the pH, that's when we use the power of 10. 10 to the,
I'm next.
yeah.
This is correct. So, okay. Or not.
Yes.
It's correct. Okay, how can I check my log? If I want
So
to
if you take the negative log of this number, it should be 3. And that's it.
check like 11 minus 3 or minus.
No, the negative log of what you wrote. So 10. 3. That should be this.
So after I answer, I can do it like that to check.
Yeah, check it. Yep.
And if they not give me the number,
Mm-hmm.
like the 3,
Mm-hmm.
I can do it by both of them, the log, like.
Right. Right.
And HB valence by 10.5. What they mean for that? Like, what I can use this number for?
I think that just tells you where in the book you can find that kind of problem. It's from jump from section 10.5. Yeah. All right, so yeah, this one, the first, the H3O plus should be 10 to the minus 3, hydroxide 1 times 10 to the minus 11. Then B, it would be 10 to the minus 6 and 10 to the minus 8. The only one that could be tricky here, the last one, because we have this decimal, so we should really put that, once you do this problem the exact same way, but then put the number in the calculator and see what it comes out to. So we would say here that the hydronium ion concentration is 1 times 10 to the minus 9.20 molar, and the hydroxide is 1 times 10, to the minus 4.80 molar, but we shouldn't leave it like that. We should calculate that and see in better numbers. So, whoops, where's my calculator? There we go. So we should go 10 to the minus 9.2. So that's 6.3 times 10 to the minus 10. And the other one, 10 to the minus 4.8 is going to be 1.6 times 10 to the minus 5.
So we cannot leave it like that.
Right. Yeah, put it in your calculator to fix it. All right. Let me stop there. If you have more questions, I will definitely be here tomorrow. So come by if you're having trouble.
So about his name and like how make this thing and figure out the A's and B's.
Yep.
That is the case.
That would be the quiz, yeah. Did you get it to work?
But give me like a number or a number.
That's right, yeah.
6.3. But then we count all of them, like we will take the minus and this one, or not, like this one.
Yeah, one is for this and one is for this. It depends. Maybe the question will say both, maybe the question will say one or the other.
He said like H3 plus, so we have only this number. But 10 with 5, so it will be 15.
Right, but because of these numbers, it's not really, because these are not one, so it doesn't really hold.
It's really just I think it's simple. Like this.
So today we reviewed like all what we have in the quiz here.
Yeah, yeah.
Mhm.
And here we should know like a